ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Here we had, in the last class, we had looked at what is called as total Lagrangian formulation, and we had said that there are two types of formulations that you can follow. One is an updated Lagrangian, and another is a total Lagrangian. We had a discussion about this. So we had looked at the total Lagrangian formulation. We were halfway through, and we realized that there's a lot of algebra that is involved in the total Lagrangian formulation. So let's just quickly look at what these are, okay, before we go further and look at the finite element formulation for the total Lagrangian. So we write down the functional, all of you are familiar with it, functional in terms of the original configuration or reference configuration. And of course we have two terms, you know this. So essentially what we did was to now find out the first variation of the terms that are involved in this W. So in order to do that, for example, for this it was straightforward, that is the variation of the external loads or the potential loss due to external loads. So here we found that if we have to do this, we have to have a small jugglery or algebraic manipulations that have to be done. Or in other words, this term now has dou W by dou Cij. See, of course, this can also be expressed in terms of Eij. We will see that in a minute. So in order to do that, we may have to have some formulas in place for this manipulation. So say, for example, if I have half delta Cij, delta Cij Sij, which can be written as delta Eij Sij. So we need to have what, or we need to know what this is. In order to do that, okay, we will substitute, or we will first find out what is the first variation of f. This first variation of f comes from the fact that f can be written, okay, in terms of the displacement u, okay, or in other words, if you want further going down this, you can write x is equal to u, or x minus x is equal to u. X is equal to u plus x. From here, you can write down dou x by dou capital X. You can write that down in terms of, say, from here you can write dou x by dou capital X. Of course, this is a tensor, is equal to dou u. That is, here it comes ui comma capital I and so on, okay, plus I. That is the term which comes here for f. Okay, so from this you get here, okay, and you use and you see that the variation of this is equal to 0. So you will get delta u, delta fi is equal to delta u I comma capital I. Okay, of course you know that small I is in the current and the capital I is in the reference configuration. So with this, okay, now with this, what we do is to look at the first variation. This is an important thing. First variation of E, which is the our Green's train, okay, then you take each of these terms. Of course, we know that Eij is equal to half of F transpose F minus I. So you apply the variation for F transpose and F, so you will get two terms, and of course the variation of I goes to 0. Okay, so these two terms are now taken, or this is taken along with Sij. So and then, or in other words, this is multiplied by Sij. So you will get, using the symmetry of Sij, you will get a term like this. Okay, then now using the derivation which we have done now on the first variation of f, okay, along with this, and then using the Green's theorem, ultimately you get delta phi to be written in this fashion, okay, from which we said that, what is that we arrived at? We said that yes, exactly. So we can get the equilibrium equation. Of course, this is the whole thing. We will get the equilibrium equation, okay, this and we will get the boundary conditions from this. This is what we saw in the last class, and we also said that delta E, for example, if it is to be written in terms of 1 1 2 2 3 3 1 2 and so on, you can write down delta E, okay, to be like this. So this will be the starting point of our finite element formulation. Is this clear? Now, if you closely look at it, if you look at the concepts, forget about the terms that are involved, they are no different from what you did in your earlier class. They are the same. The only difference now is that the type of strain measures and the stress measures that you are using, the stress and the strain measures that you are using are different. So that involves lot more algebraic jugglery. So the concept is exactly the same. Okay, there is no difference with it. But because of these large number of terms, the expressions becomes extremely complex. Is it clear? Okay. Now we said that we can go and do the finite element formulation straight away from this, right? The finite element formulation starts with writing down x in terms of, say, the xi in terms of the sigma, what's it, shape function times the x nodal, very good, in terms of, so I am putting alpha here, where alpha is summed up to the total number of nodes, okay, and so this is alpha I and so on, right? So this is our regular formulation for the isoparametric element formulation, which we had used again in our earlier classes, so that now U is again written in the same fashion, okay, Ui, if you look at Ui, then it's again written in the same fashion, n alpha U I alpha and so on, where again alpha indicates the nodal quantities, right? Is there any questions? Okay. Now essentially what we are doing now is, don't note this carefully, forget about for the time being the algebraic manipulation. We are exactly following again the same procedure. Only thing is now we are going to get all the terms that are involved here, okay, from the discretized quantities. All the terms there we are going to obtain from the discretized quantity. Now, for example, if I have to have ui comma, of course, I, so what do you do? The same thing what you did in your earlier classes, and that is what resulted in, for example, the B matrix, right? Now B matrix is slightly going to be different, okay, but the concept of B matrix is very similar. So that this can be written as, again, n alpha comma I ui alpha, right? Is it clear? Okay. Now what we do is to substitute this into this expression in order to get a B matrix. Now actually let us see, let's just do that. Let's see what we get. Is there any question so far? Clear? Now let us write down for each of the nodes. Let us take a 3-dimensional problem, because this is a 3-dimensional element is what we are looking at. Because delta E we have written in a column as a column vector with 6 entries. So what we are looking at is a 3-dimensional formulation. Okay. Now for the 3-dimensional formulation, let us say that we have, okay, each node has of course 3 degrees of freedom. Let us say that, let us call that as say delta u1 alpha, delta u2 alpha, delta u3 alpha, where alpha is the nodal degree of freedom. Okay, let us see what we get. Let us say, look at the first expression here. Okay, now what I do is look at this first expression. This is where some doubts were there. From here I substitute it into this expression. Okay, note that from here I substitute it into that expression. Note that I is repeated, okay, so that you will get actually there. What is that you will get? So substitute that, say f, let me just take that first term, what we had written, fi1 delta u I comma 1. Okay. Now, how do I now get the first term in my B matrix, what we had written in the last class? I'm giving you a clue. Ui comma I, we had written this as sigma n alpha comma I ui alpha, right? So substituting this into this expression, okay, we get actually a big expression for sigma. For sigma, we will get a big expression. Let us just substitute that. So this here. So what are the terms you have? You will have f, I think it's going to be really big, f11 into, okay, delta u11, okay, delta u11. So that I have to obtain from this, okay. So delta u11, which will involve alpha 1 u1 alpha, right? Sigma of n 1, okay, u1 alpha. Since this is delta here, I will get delta u1 alpha. Is this clear? Plus, what is it that I will get? Second term, plus f 21 sigma n alpha comma 2 delta u 2 alpha, right, plus f31 sigma n alpha comma 3 delta u 3 alpha. No, sorry, alpha comma 1. 1, 2, 1. Yes. Alpha, yes, sorry, 1. Yeah. 1, 1. Correct. Because that 1 is constant here. Yeah, okay. So this sigma where is summed up by from alpha. Okay. So this will be like n1 comma 1 delta u1 plus n2 comma 1 and so on. It will be a big expression, right? So in order not to write the whole expression, we split this B into B alphas. Okay, we split this into B alphas. That, say for example, this we split it into a number of alphas, okay, properly aligned, where each of them belong to one node. So then comes my first expression or first delta E term. So that will be, that is first, that is B delta E terms in terms of B alpha. Of course, some of them can be written as from here, first term f11, okay, n alpha comma 1, f11 n alpha comma 1, okay. Let me multiply that by delta u1 alpha, delta u2 alpha, delta u3 alpha, and of course sigma of alpha I have just taken it outside, right. Then the second term will be f21 n alpha comma 1, and the third term will be f31 n alpha comma 1. That's the first entry here, right? Is this clear? That's the first entry. So you can imagine how big it is. Now the fourth entry which is there is going to be still more bigger. I would like you to complete it. This fourth entry here. Okay. Can I give you 2 minutes? Can you write down and tell me what it is? Though these are not important from concept wise, but I just want you to understand how it is written. So f u I comma 2. So f11, first term will be f11 delta u I comma 2, you have to put n alpha comma 2. That will be the first term plus the second term plus I2, Fi2. Note this here. Note this here. So that will be plus F12 delta U. Now again alpha comma 1, very good, alpha comma, sorry, delta n, not delta u, n alpha comma 1, okay. This whole thing will be multiplied by delta u1 alpha, right. This will be the first term. Then there will be a second term, there will be a third term. The second and the third term will be terms which will be multiplied by delta u2 alpha, delta u3 alpha. Okay, so this whole thing can be, forget about this, you can fill this up, it's not a problem. Or, I mean, you can get this matrix also from all standard textbooks give this. You can look at Zinkiewicz for this. But ultimately what we get is that this can be written as, say, B alpha, this alone, one term alone, into delta U alpha. Is this clear? Now, if you look at this, actually this can be split again. Now, I'm not going to do that. I'm split again into two terms. Actually, this has L term and NL term. Or B matrix can be split into a linear part and plus nonlinear part. Okay, so linear part is the same as what you did in the previous course, and there will be a nonlinear part. Okay, my next step is exactly the same as what we did in our earlier classes. What is that we did? We substituted this back into my expression for the variation, first variation, in order to determine k. Okay, so I substitute it back into my first expression what we wrote. Okay, and then let us see what happens for delta phi. Okay, substitute that into that expression and take delta u alpha out. Remember, this was very similar. Now, only thing is this alpha I am writing there, okay, just to state that since it is big, I can't write 1b. Next step, I'm going to just write that down. But just stating there because sum up, you have to sum up with respect to each of the alphas. Yes, dV minus f alpha is equal to 0. This was exactly the way we had written before, and this gives rise where f alpha is, of course, okay, if you want a matrix, okay, and f alpha is, of course, the ones which consists of the body forces and the surface forces. Right. In other words, this is my starting point for what? For the Newton-Raphson scheme. Remember that this is the starting point for my Newton-Raphson scheme. If you remember, these terms where B transpose sigma, delta U was outside, B transpose sigma minus F is equal to 0. If you remember, this is how we started Newton-Raphson. Let me write it in the same vein as we did last, some time back. So where we had B transpose sigma. Remember that we had put this as B transpose, okay, dou sigma by dou epsilon and so on. But right now, I can't write that next step in the same simple fashion as we did before. Because this B, in fact, B, if you had noticed in my last session, when I wrote the Newton-Raphson scheme, B was well behaved, nice guy. It was independent of F's. There was no F, independent of U. So I was able to write this as, how did we write? B transpose dou sigma by dou epsilon into dou epsilon by dou U into delta U. So that we had KT, if you remember, we had a lovely KT term without much problems, which was B transpose DT B. This is for small strain nonlinear problem. This is the KT we had. But now this B has or is much more complex than what it was in my small strain problem. So let me write down, now that you know what this B's contain. B contains B alphas. We can write this down as, say, for example, B transpose S, okay, all the sums of it, okay, I hope you will do the correct this one, dV minus F is equal to 0. Okay, this is my starting point for my Newton-Raphson scheme. Now, how do I write this down? What are the terms that are involved? Now, let us see what these terms are. Okay. Now, in other words, what do you think would be the difficulty now? Or what are the other terms which I have to add than what I had done in my previous course? Let's see whether you're able to say that. Now, since B involves U, okay, and F may also involve U, actually, when I want to calculate KT, I will have 3 terms. One term involving, okay, first term is very similar to what, say, for example, similar to what we did in the last class, that is B transpose dou S by dou U. Okay, that can be written as B transpose dou S by dou E by dou U. Okay, so transpose dou S by dou E by dou U dV. Of course, delta U is there, so but I am writing only KT. Okay, plus what's the other fellow? Dou B transpose. Now this has U in it. P has U in it. This is how we had written down. Okay, because it has deformation in it, F in it. So that term also has to be differentiated with respect to U. So that term will be dou B transpose by dou U S term. Okay, dV. That's the next term which I will have. And f is not going to be, or f may or may not depend upon u. F may depend upon you. I will come to that in a minute, what it is. So that term also will be there. Okay, we will investigate each one of them and what they mean. Is it clear what's the difference between this and small string?
How F contains U, capital F contains U.
Yeah, we'll come to that in a minute. How does this term come into picture? We'll name each one of them. This guy is due to the material contribution and is called as the, if I put KT, is called as the KM matrix, the first guy here. Okay, that's the material contribution. The second guy here is due to geometric stiffness. Okay, that's the beauty of this whole formulation. You can understand each one of these terms. First one is there is a material contribution to stiffness. The second term, note this, this is due to B which has F in it. So this is what is called as the geometric contributor for stiffness. And the last term is due to the load, and that is called as the load contributor to stiffness. So you have, because we have split this PL plus BNL, or in other words there are nonlinear terms associated with B, that means that the stiffness matrix has contribution from geometry or geometrical changes as well. Now these are what are called as the stiffness terms due to load. Now sometimes people call this as follower forces. Follower forces. Now how does it change, or why is there? It's a very good question. Why does it contribute suddenly to the stiffness? Now let us see that. Let us just understand this term first, and let's come back to this question in a minute. Okay, let's first understand this term, what it means. Suppose I have a cantilever beam and I apply a load. Okay, now if it's a very small deformation, you won't have even bothered to ask a question whether the load is going to act in the same vertical direction, or is it that this load will act, say, normal to it. Okay, when the deformations are small, you won't even bother to do that. Say pressure is acting onto a surface. Okay, now if the deformations are very small, you wouldn't bother much to look at the pressure. If you are defined, for example, pressure in terms of x direction, you won't define, or you won't bother if this x directions there is a change. But on the other hand, when the deformations are large, okay, the pressure which, say for example, was acting like this, okay, where, say for example, this is x direction, or this load, okay, which was acting the downward direction, if these deformations are large here in this cantilever or on this pressure, then there may be a large variation in the way the force acts. In other words, there was no horizontal component to this when it was like this. But when the deformations are large, there may be a horizontal component to it, and so on. So in other words, the load follows the deformation. Okay, which means that F terms varies with U. So that is the contribution for the stiffness matrix, and that is what we call as follower forces. Yeah, any questions?
So this F term is outside that integral, or it's inside that integral?
No, of course it is outside. B transpose sigma minus F, okay, is the side term. But when I take dou u, okay, dou psi by dou u into delta u for my Taylor series expansion, then dou f by dou u into delta u will come here. The previous case it was not there.
Then when you are doing this one, then this term will be left.
Yeah, that is why this is not inside the integral. It is outside, dou f by dou u term. So that is what is the contribution for my KL term.
Sir, Here, the force always reduces the stiffness of the entire system. Is there any system
Force reduces. I am not. I didn't comment.
that have minus term?
Yes.
Minus dou F by dou.
Yeah. Yeah.
It reduces the stiffness of the entire system.
Yeah. But I don't know how the dou F by dou U is going to vary. Whether that is going to be negative or positive. So you can't make generalized statements whether the deformation reduces stiffness or not. Very interesting example.
But here it will reduce the stiffness in this system. What we have drawn.
Yes, but you can't make very general statements whether deformations. You can't make a general statement that deformation reduces stiffness. It may not. I will tell you a physical example that will make things clear. So in other words, why you can't make a statement with deformation will a system stiffness decrease, right? Suppose I have a sheet of paper, okay. So let us say that we take this cloth, okay. The cloth is I'm just holding it just like this, no loads are applied, right? Okay, you apply the load on top of it like this, right? There is going to be some deformation. Suppose now I deform this cloth like this. I apply load in this direction, okay, and even in a biaxial way, both directions. I apply a load, right? Now this cloth is now deformed. Now if you apply the load perpendicular to the cloth, what will happen to this cloth? The deformations are going to be less. So in other words, this has been stiffened by stress. It is called a stress stiffening. Okay, the deformations in the other directions had actually, in fact, enhanced the stiffness of this cloth. Okay, in a perpendicular direction, right? So that's why you cannot make a general statement that deformations reduce stiffness. Is this clear? Okay. So these are the three terms that are involved, and they are called as Km, Kg, and Kl terms. Now, let us go to the next step of defining it for updated Lagrangian. How do you define this whole problem of updated Lagrangian? No different, very straightforward. The only thing what I am going to do is transform all the quantities which I had written to the current coordinates. What is the current coordinates? Current coordinates are small I, but current coordinates in this case is actually not Eulerian, but the converged state at say Tn. Let's say Tn, time step n. This is actually what is called as the current configuration. In other words, you update all the coordinates, okay, of the body to the current or Tn by adding to the coordinates the displacements, the total displacements, right? So let us see how we are going to transfer this, right? How are we going to transfer all the terms, not these terms. I mean, we have to go back to my original statement where we had, say, delta Eij, Sij, okay? Let us see how we are going to transfer. Let us take that term. So what we do term by term, I'm going to transfer. Okay, I'm going to carefully transfer this to the current coordinate system. So let us take, because of that, let us take delta Eij, the first variation of Eij. Let us see how you can write that. Of course, what is it that is going to be useful to us when we transfer it? Deformation, F, very good. Okay, where are these kind of things that we did? Note, we did this when we did Nansen's formula. Okay, we did a similar thing when we calculated dV to capital dV ratios, d small v to d capital V ratios, where we did similar pullback operations and push forward operations. What essentially we did was to play with the current coordinates and the deformed coordinates. Let us see, we will do that. Let's see how we write this for updated Lagrangian. Okay. Unfortunately, I don't have them on the board, so the old ones. So you may have to write it down. from your notes. Let us see how you are going to write down delta Eij. Let's do a small exercise. You just try it out. So, delta Eij, we had written this, right, some time back. So, how did I write it? Half of delta Ui comma j into, or I'll add this and multiplication I'll do it ultimately, delta U j comma I into f I f j j. Now look at this term, what is inside? What is inside? That is nothing but delta epsilon ij. So delta epsilon ij f I f j j. Look how neatly the whole thing falls in place when we move from the reference to the current configuration. Now let me Eij, Sij. What happens to this term? Let's see how many of you are able to recognize and say something. Sij. Second, pure law Kirchhoff stress. Yes. So what is the relationship between the second pure law Kirchhoff stress and Cauchy stress? Sigma is equal to F S F transpose 1 by J, or J inverse. Okay? Or in other words, F S F transpose J, F S F transpose equal to J sigma. Let's say you are able to recognize any of them here. Look at what these three terms in indical notation means. Fantastic. So that is it. So this is equal to dou epsilon ij into j sigma ij. Is that clear? Okay. So now what is that you do? You go back and substitute for my delta Eij Sij in my previous expression for delta phi. Let's see what you get.
Actually, capital Aj and Sij should be equal to epsilon ij into sigma ij. No, j should not.
Why? How come? How is that possible? So what we have essentially what we have done is to
No, this is something like a scalar quantity.
absolutely. Please note, yes, very interesting question. So why did I get J? So if I look at the total energy term,
That should be same.
yes, but when I look at the total energy term, delta Eij Sij d capital V is what I have there. Okay, when I integrate it, I will have now small dV. Okay, so if I now substitute it back into my expression, so that's why I said you have to be careful and they are not blind transformations. Okay, go back and put this. It's a very interesting thing. So you put this back into my first expression there, delta Eij Sij term. So you will get delta epsilon ij, okay, sigma ij, j d capital V. Okay, so that j d capital V will go now to small dV. So now what was omega 0 now, when I now convert this into small dV, will go to the current configuration. Okay, of course you will have this is my delta phi, you will have minus delta phi external. This is my first variation. Okay, the first variation should be equal to 0. Right, is that clear? Okay, so you have to be careful in converting every term. So in the same fashion, when if I write it in terms of say dt delta Eij, so integral delta Eij, okay, when I differentiate it and write it as say dt into dE, okay. So in other words, this dt is the relationship between delta S and delta E, okay, and write this as Ijkl into dekl, okay, dV. Now let us see if you want to, this is my first term for my k expression, okay. So let us see how you write this. Substitute this one by one term and see how you write this. So this has to be d delta epsilon ij dijkl. This is a small catch in what we are doing, into delta epsilon kl, right? Okay, but note that we always define, okay, d capital Ijkl or dt to be delta S by delta E. That is how, that is the theory. So I have to calculate an equivalent d in the current configuration. In other words, note this carefully. In other words, we know how to transform stress. We know how to transform strains. Just saw it. Okay. How do you now transform the D, that is capital D? If I can call it as the tangent modulus, tangent elastic modulus. How do we now transform this? Because usually you are given only D capital. If you look at most of the strain energy forms, all the strain energy forms that you write, okay, say W is a function of E only. Okay, obviously you can't write that straight away here. You have to transform it to the current configuration. Please do that. Let us see. That
pushback forward operation of
you need not do pushback pull forward. Right now. Yeah, actually that is what it means. But let us see how you arrive at this. Just substitute it. Or in other words, how am I going to write delta epsilon ij if I write, say, with respect to small d as the one which belongs to as the elastic modulus for the current configuration, Ijkl d epsilon kl, then what is this relationship with respect to this? That's the question. Not very difficult. This is delta epsilon ij fii fjj. Right? And this guy here is d epsilon kl fkk fll. Substitute that. So I define, note this carefully, I define dijkl, okay, to be fii fjj fkk fll into dijkl. The only other thing that is there is dV is equal to jdV, and usually that is also included here, so that not here, the next one, here, so that j into dijkl is equal to fii fjj fkk fll into dijkl. So that is how you find out. I mean, this is very, very important expression. Okay, let me write that. That's how you find out the elastic modulus in the current configuration. J dijkl is equal to Fii, Fjj, Fkk, Fll, d. No, but we are in the indical notation. No, we are in the indical notation. We are not in matrix notation. Matrix notation, of course, will have an effect. These are all indical notations that we are doing. Okay, to make things clear, okay, so that you will know where the summing up and so on happens. Okay, we are doing the indical notation. Now, of course, we will have a look at the kg term slightly more closely in the next class. Okay, so that also has to be transformed. Okay, that term is usually called as G alpha beta term. Okay, we will look at that thing in the next class. But before that, what I want to comment is a very important comment, that by this time you would have realized, that both the updated and the total Lagrangian formulations are equivalent. There is no difference between them. They are the same. Okay? Basically, because mathematically, in a very correct fashion, we are trying to get from the reference to the current to the reference, and so on. So no way we miss out anything in this. So the results should be the same. So it's almost meaningless to talk about whether updated Lagrangian is better or total Lagrangian is better from an accuracy point of view. But at the same time, please note that these guys here reduce to such a nice extent, okay, and so close to the linear formulation, linear, not only linear, even non-linear small deformation formulations, okay, that the extension of the code from or implementation of the code from linear to nonlinear is very simple with updated Lagrangian. Okay, though we have note that it is not just that if you put delta epsilon ij, I will get the current configurations small deformation code, because there's one more term which we have to look at that. So I told you we'll have a look at it in the next class. So, but the whole point is that the only difference or only major advantage for this formulations are that they are easy to implement. Okay. Is there any questions? Okay. The second term, we will expand it and we'll have a closer look in the next class. And we will finish the finite element formulation. But before we close, there's one more comment just coming up in the next class, that this is only a displacement based formulation. But unfortunately, very unfortunately, many of these formulations may not be valid if you do large strain, large deformation problems. Very good. There are problems where the problem can be geometrically nonlinear, okay, but the strains can be small, okay, so that we can still use an elastic type of constitutive equation, but add the geometric part of the stiffness matrix. In other words, this formulation is also valid for linear elastic case when the strains are small, when the displacements and hence the geometrical variations are large. Okay? So that kind of problems, there are quite a few problems that exist. For that kind of problem, you can still use this formulation. But when the strains are large and the displacements are also large, then we have certain problems which we have to take care of. We'll see that in the next class. Okay, we'll stop here and continue in the next class.